Currently, we do two checks for the tower column when looking at it as a beam. For its flexural capacity or bending, we check the capacity of a reinforced concrete beam section, and we also check the minimum reinforcing in the section requirement. So first, let's calculate the moment capacity. From ACI 318 Strength Design, Section 9, in the notes provided, the nominal moment capacity of the section can be found as Mn equals AS times Fy times D minus A over 2, where AS is the total area of steel, Fy is the yield stress of the steel rebar, D is the depth to reinforcing, which we'll take as the furthest away, or the bottom steel, because that is what is actually ending up in tension. And A is the width of the concrete compressive block. And these can all be viewed in the diagram here. Design assumption number 6 in the code, the relationship between concrete stress and strain, can be modeled as a rectangular distribution, allows us to calculate A as ASFY over 0.85 times FC times B, where F prime C is the concrete compressive strength that we should already know from our load material properties, and B, in our case, is the column section width of 40 centimeters. And this is the equation here. So in tier 2 checks, we just compare this nominal capacity to our moment demand from cable forces with allowable strength design using a factor of safety of 1.5. In this case, moment demand comes from cable forces only. Unlike overturning moment, we're checking the forces in the reinforced concrete as a material, shown in the free body diagram here. The self-weight of the tower is not creating any extra flexural demand. We'll take the unfactored moment to be negative PV column times the offset plus PH column times the column height, which you can see here on the right. Now, allowable strength design, ASD, is very outdated for reinforced concrete. And to follow the full LRFD, load reduction factor design check, we will compare our design strength to our required strength. Design strength comes from our factored nominal capacity of 0.9 times Mn. Because this is a tension-controlled section, we can use table 5-2 from the code to take 0.9 as our load reduction factor. Required strength comes from load factors multiplied by our service load effects. Our service load here being MD and ML, and our load factors being 1.2 and 1.6. So we'll take this to be 1.2 MD plus 1.6 ML. More information about the specifics can be found in section 9.1 of the provided ACI 318 notes document. But note that this requires us to split our cable forces into dead load and live load contributions. Make sure not to use full load instead of live load, because you will be double counting. You probably have already calculated these cable forces from dead load in the past in BP211, but you will have to go back and split these up and then redo the forces on a single column in order to have those split contributions that we can add separately. So I note here, dead load and live load will be different based on the loading we use to calculate all the way back in our cable analysis that pH term. Next, after we've calculated and checked moment capacity from a strength perspective, so this equation here, we also need to determine its adequacy from a serviceability perspective. As seen in the moment deflection rate relationship below, the cracking moment will occur before the ultimate failure of the tower column, or that capacity we calculated. From a serviceability perspective, this is not ideal. Cracks in the tower will not inspire confidence in the community members. So from equation 9-9 in section 9.5.2.3, the ACI 318 notes provided, we can get our cracking moment as MCR equals IG times FR over YT, which simplifies the cracking moment as S times FR for our rectangular section. The cracking moment is a deflection check and signifies the point at which the section would begin to crack. So S is the section modulus, computed as BH squared over 6, where B is the effective section width of 0.4 meters and H is the effective column depth of 0.7 meters. FR is the modulus of rupture calculated by equation 9-10, which is 7.5 times lambda times the square root of F prime C, where F prime C from our loads and material properties is the concrete compressive strength in PSI in this equation, remember. And then we can convert back to megapascals. And lambda is a modification factor. And we'll take that as 0.85 for sand lightweight concrete. After calculating the cracking moment, we will use that to make sure our minimum reinforcing is adequate to avoid cracking due to tension in the beam. To do this, we will compare our design strength. Remember from above, this is just 0.9 multiplied by our moment capacity with our cracking moment we just calculated and the required strength, which from above is the load combination. To do this, we'll compare the design strength with the minimum between, with the lesser of 1.33 times the required strength and the equation below, which is gamma 3 times gamma 1 FR plus gamma 2 FCP times S. Now, these factors come from the NCHRP and are summarized in the presentation linked below to an AASHTO committee. But for 2011 onward, the required comparison for overdemand is that 1.33 times the required strength here. And the required comparison for section demand for cracking is that longer equation. But that can be simplified to gamma 3 times gamma 1 times FRS because our steel is not pre-stressed. And then FR and S are the cracking moment, so we can just apply a factor of gamma 3 times gamma 1 to the previously calculated cracking moment. Now gamma 1 is taken as the cracking factor of 1.6, and gamma 3 depends on the ratio of yield strength of the steel rebar to the ultimate tensile strength of our steel. So for grade 40 steel, this is going to be 0.67. And this whole equation again is spelled out on slide 15 of the presentation provided. So this was a lot. And remember, we're checking the overall capacity of the tower section as a beam and its serviceability through deflection. So capacity here based on this moment and serviceability based on this deflection. In the following section, we'll view the tower as a column and check its axial and flexural capacity combined. So the flexure, due to this force being offset from the center line here, as well as its general axial capacity as a column from this force here.